Welcome back. This is Chapter 1 of Calculus, Chapter 1, Section 1. Chapter 1 is all about this topic of limits that we see at the very end of pre-calc and the very beginning of calculus. It's one of the four main components of calculus and is actually what most of the rest of calculus is about. So in this chapter, we're going to look at the idea of limits. This first section, we're going to be looking at the notation and the definition and seeing what limits are graphically without ever really dealing with equations. We'll get into dealing with equations and how to find limits from that in the second section. So we're going to look at what are limits. We're going to see a few definitions of limits, and we're going to be building our understanding of what limits are. So first of all, what is a limit? In general, a limit is what you would expect a function to be at. If you had to cover up that value, what would you expect it would be based on everything around? So, for instance, if we were looking at this function, we can look at, say, when x equals -2. What would we expect this function to be when x equals -2? Well, it looks like it would be about -3. And in fact, it is. The notation here, we can write the limit. It's a LIM for limit. I don't know why. I always write my limits in cursive. I've tried not doing it. Limits and logs. It really gets confusing when we have the limit of the natural log. Notice the limit has an I, the natural log does not. But I've tried not writing it in cursive. It doesn't work for me. So we have the limit, and then now below it, not quite a subscript, but kind of a subscript, but actually below it, we have our variable x, and then an arrow, and then our number. We're looking when x is -2 of f of x. We'll call this function f of x. I did not label it earlier, but we'll call it f of x. So the limit as x goes to -2, or as x is approaching -2 of f of x equals -3. So as we're kind of breaking this down a little bit, this right here is our x value, and this over here is our y value. So that's when it's approaching -2. Really quick, you probably won't even need to pause this one because you can see this just by observation. What if we wanted the limit as x is going to 0 of f of x? What value would that be? Do you have it yet? So if we're looking at x equals 0, we're looking right there. Oh, that equals 1. Or it looks like it equals 1. In fact, this graph is meant so that it all is what it looks like it equals. So as x is approaching 0 of f of x, it's going to 1. So that's kind of the idea of what a limit is. This is what we're going to be looking at. It does get a little bit trickier than this, but not particularly. So one of the things you'll be doing is knowing what this means. So if I gave you the question, you would have to know what this means, the limit as x approaches 2 of f of x, and be able to say, like, let's see, x equals 2. Oh, this is -1. The other thing, so being able to read the notation, but also writing the notation, like your answers should look kind of like this, like the whole thing. Like the answer is not -1. The answer is the limit as x approaches 2 of f of x equals -1. So what is the limit, or the notation? So the limit as x approaches c of f of x equals L means that as x approaches the value c, the function approaches the y value, L. This is called the limit of the function as x approaches c. This is exactly what we were just looking at. This is just the more formal definition. More limits. So if we have a function, say f of x equals x squared minus 9 over x plus 3, a nice little rational function, and we want to find the limit, we want to find, say, the limit as x approaches negative 3 of f of x equals something. We don't know what it equals yet. Right now, we don't know how to deal with the equation. And that's right, that's fine. We'll deal with the equation in the next section. But right now, we're going to graph it. So let's graph this. We pull out our graphing calculator, and we graph it. It looks like this. All right, well, that looks kind of like a line. But, rational function looks like a line. Okay. Well, we're looking for negative 3. It looks like it's right down here. But we don't have to just look at the graph, because especially with rational functions, things can be weird. Like if we put in negative 3 here, we're going to divide by 0. And so, all right, well, let's look at the table. All right, so we pull up the table. All right, so let's see. It's going from negative 10, negative 9, negative 8, negative 7, error. This is the part we're looking at here. And then negative 5, negative 4, negative 3, negative 2, negative 1, 0. Now, so if you remember, I said the limit is what we would expect the function to be based on everything around it. Looking here, we'd expect that to be about negative 6. That would make sense. It falls right in line with the pattern. We're still a ways out, though. We're going by every 1. A lot could happen in between x equals negative 2 and x equals negative 4. So we could zoom in on the table. To zoom in on the table, we go to the table setup. I'd start your table at the value you're looking at, because that'll put it right about in the center, or it'll put it on top and you can easily scroll. If we started at 0, we would have a long ways to scroll before we got to what we were looking for. And then I have the table going at every 100th instead of every 1. That's going to zoom in on the table. And so we go back to the table now, and we get this. So now we're not going from negative 2 to negative 4. We're going from negative 2.99 to negative 3.01. And we still have an error, but again, based on everything that's around it, it looks like the limit as x approaches negative 3 of f of x should equal 6, negative 6. And in fact, it does. So that's another way you can look at limits, especially if they're just kind of weird looking, like if they don't show up really nice. And right now, if you have an equation, this is the method that you know how to do. We'll fix that in the next section, show you other ways of finding it and dealing with the equation so you don't have to graph it every time. But right now, we're just looking at it visually. So we also have these things called one-sided limits. So now with a limit, like the full-on limit that we saw in the last one, it was going to negative 6 from both directions. A one-sided limit is just looking at one direction. And so we have two. We have the left side, and the way that we notate this is we have this little exponent on the C. It's not actually an exponent. It's just like an index type thing. It's telling us which way it's going from. So it's going to C, x is going to C from the negative, from the left, or x is going to C from the positive, from the right. So the left side is as it's going this way. The right side is as it's going this way. So what does this look like? Well, here's a graph. Now, if it makes you feel any better, I had to graph this function like with equations. I had to figure out what equations to use. So this is fun. So we have a few different places to look at. Now, looking at places like x equals negative 8, that's boring. All right, it's going to be right down here. We're looking at places like, let's say, x is negative 5. So we're going to find the limit as x approaches -5 from the left of f of x, and we're going to find the limit as x approaches -5 from the right of f of x. So from the left, we're looking, if we're following the line this way, where is it going to? It's going to right here. That would be 1. From the right, we're looking at following the line this way, which is going up here, which is going to be 3. So the left side limit, as x is going to -5, is 1. The right side limit is 3. We have a couple more here. We have as x is going to 0. Let's look at that one next. Limit as x is going to 0 from the left of f of x, and the limit as x is going to 0 from the right of f of x. So take a second, look at it. What do you think these ones are? So as we come from the left, we're going this way, and we're getting to -2. From the right, we're following it this way, going to 1. All right, we have one more interesting place here, and that would be at x equals 3. Because, let's see, we have limit as x is going to 3 from the left. We have the limit as x is going to 3 from the right. So it's going to 3 from the left. We're going this way. Well, it looks like it's going to 1. From the right, we're going this way, and it's also going to 1. All right, but there's a hole there. That's okay. There's a hole on that last one too, at -3, -6. The hole does not affect the limit. Now, we'll be talking about what this is. Like, this is not a continuous function. That's for another section later on in this chapter. But the limit itself is the same from both sides. In fact, if that's the case, a limit of a function is said to exist at x equals c and equals L if and only if both one-sided limits go to the same thing. So since these two are the same, that means the limit as x goes to 3 of f of x equals 1. For these other two, the limit does not exist. Because it's going to different places. So back to that original definition, it's what we would expect to be there. Well, if we're looking at, I'm gonna erase some of my scribbles here. If we're looking at -5, and we're looking at a table, this side is getting closer to 1, this side is getting closer to 3, and so the table's going to have a big jump in it. What would we expect to go in that spot? There's nothing that we would expect to go in that spot. Like, it just doesn't make sense. And so the limit itself does not exist. This is the formal definition of a limit. Like, this is like the really official definition. And so we have limits, we have one-sided limits, and we're also going to look at infinite limits. This is something else that can happen. So we get functions like this, which have our vertical asymptotes. So we have vertical asymptote here. Now, these limits do not exist because the y value is not getting closer and closer and closer to something. However, we do say that the limit might go to infinity or negative infinity, knowing that the limit does not exist, but it does tell us stuff of the function. It's telling us that it has a vertical asymptote and it's either increasing without bound or decreasing without bound. So it's either going up or going down at that point. So if we're looking here, this would be at, say, -3. The limit as x goes to -3 from the left of f of x equals infinity, and the limit as x goes to -3 from the right of f of x also equals infinity. Sometimes I've seen them written as 1 is just the limit as x goes to -3 equals infinity. That's not particularly good. I would keep them split up as the separate limits. And then for this other one, it's say 3. Limit as x goes to 3 from the left of f of x. That's coming from this direction. It's negative infinity. And the limit as x goes to 3 from the positive, so from the right, so it's coming from this direction, is going to be positive infinity. So that's just how we notate those infinite limits. Again, the limit itself does not exist, but it tells us what the function's doing, so it can still be very useful. So this is all that there is to section 1. You're looking at graphs, and you are stating the different limits, being able to read the notation, being able to write the notation, and looking at the concept of a limit without getting bogged down in equations and functions and stuff like that. So, until next time, keep working problems, keep asking questions, and as always, happy mathing.